Welcome to the problem walkthrough for LeetCode problem number 120, triangle.
In this session, we'll explore how to solve this classic problem step by step, covering its intuition, approaches, and complexities.
Let's dive in.
In this problem, you're given a triangle represented as a 2D list of integers. Each row in the triangle is essentially a list, and the task is to determine the minimum path sum starting from the top of the triangle down to the bottom. The movement is restricted to adjacent numbers in the row directly below. For example, if you're at a specific element in one row, you can move to either the element directly below it or the one diagonally adjacent to it in the next row. The goal is to compute the smallest possible sum of numbers along any valid path from the top to the bottom of the triangle.
Let's look at a couple of examples to clarify the problem. In the first example, the input triangle is structured as follows. The top row has one element, the next row has two, and so on. The minimum path here is 2, followed by 3, then 5, and finally 1. Adding these together gives us a sum of 11, which is the output. In a simpler case, if the triangle consists of just one element, like -10, the minimum path sum is simply -10, since there's only one possible path. Now consider another example with a larger triangle, starting with 1 at the top. The minimum path sum is achieved by taking the path 1, then 2, followed by 3, then 1, and finally 4. This path results in a total sum of 11. The constraints ensure that the triangle always has at least one row, with the number of elements in each row increasing incrementally. The values in the triangle can range from -10,000 to 10,000, so the solution must be robust enough to handle both large positive and large negative integers. Finally, let's address some edge cases. If the triangle has only one row, the minimum path sum is simply the single element in that row.
If all the numbers in the triangle are negative, the algorithm must find the least negative sum, which is the closest to 0.
For triangles containing very large or very small values, the solution should ensure there's no overflow or underflow during calculations.
Additionally, when dealing with the maximum size of 200 rows, the algorithm must remain efficient in terms of both time and space complexity to handle such inputs within acceptable limits.
To tackle the triangle problem, let's first consider a brute force approach using recursion.
The intuition here is straightforward. Starting at the top of the triangle, we recursively explore all possible paths to the bottom by moving to one of the two adjacent numbers in the row below. At each step, we calculate the sum for the current path, and once we reach the last row, we return the value of the current cell as the base case.
However, this approach has significant drawbacks.
Since each position splits into two subproblems, the number of recursive calls grows exponentially, leading to a time complexity of O(2 to the power of n, where n is the number of rows. Additionally, the recursion stack requires O(n) space. This inefficiency stems from overlapping subproblems, where we repeatedly compute the same states multiple times.
To address this, we can optimize the recursion using memoization.
By storing solutions to previously computed subproblems in a 2D table or dictionary, we can avoid redundant calculations. When a state is revisited, we simply retrieve its result from the memo table, drastically improving efficiency. With recursion and memoization, we reduce the time complexity to O(n squared, since each cell is computed only once. However, the space complexity remains O(n squared, for storing the memo table, and O(n) for the recursion stack. While this is a significant improvement over the brute force approach, recursion still carries the risk of stack overflow for larger inputs. To overcome these limitations, we can shift to a bottom-up dynamic programming approach. In this method, we start from the bottom row of the triangle and work our way upwards. For each cell, we calculate the minimum path sum by adding its value to the smaller of the two adjacent values in the row below.
By solving the smallest subproblems first, we ensure that each step builds on previously solved results.
Notably, we can use the triangle itself as the DP table, updating it in place to save space. This approach has a time complexity of O(n squared, and a space complexity of O(1), making it both efficient and memory-friendly. Additionally, it avoids the pitfalls of recursion, such as stack overflow, while maintaining clarity and simplicity.
Another possible strategy is top-down dynamic programming.
Here, we start at the top of the triangle and move downward, incrementally building the solution. For each cell, we updated with the sum of its value and the smaller of the two possible values from the row above. This process continues until we reach the last row, where the minimum value represents the final result. While this method is effective, it is slightly less intuitive for this problem compared to the bottom-up approach. The time complexity remains n squared, and the space complexity can vary. If we use an extra DP table, the space complexity is n squared, but modifying the triangle in place reduces it to 1. Despite its viability, the top-down approach is not as naturally aligned with the problem structure as the bottom-up method, which directly addresses the subproblems in the order they are needed. Among the various strategies discussed, the bottom-up dynamic programming approach emerges as the most suitable solution for this problem. Its space efficiency, achieved by modifying the triangle in place, eliminates the need for extra memory. Additionally, it avoids the recursion stack issues associated with other methods. This approach aligns naturally with the problem structure, as it solves smaller subproblems first by working from the bottom row upwards. A key observation here is that the minimum path sum for any cell depends only on the two adjacent values in the row below. By ensuring that these subproblems are resolved before they are needed, the bottom-up method achieves both simplicity and efficiency. While recursion with memoization shares the same time complexity, it is less space efficient due to the memo table and recursion stack. Similarly, the top-down approach is valid but less naturally suited to this problem. Ultimately, the bottom-up strategy provides the best balance of efficiency, clarity, and space optimization, making it the ideal choice for solving this triangle problem. To solve the triangle problem, we need to find the minimum path sum from the top to the bottom of a triangular array. At each step, we can move to one of the two adjacent elements in the row below. The first step in understanding the solution is to recognize the recursive nature of the problem. For any position, say, I, j, in the triangle, the minimum path sum is the value at that position added to the minimum of the path sums from the two positions directly below it, which are I plus 1, j, and I plus 1, j plus 1. This forms a clear recursive relationship. Next, we define a recursive function dfs, I, j, that calculates the minimum path sum starting from position I, j. The base case is simple. When I is the last row, we return the value at triangle I, j, since there are no rows below to consider. For all other rows, the recursive case calculates the current value plus the minimum of the two possible paths below. Using this setup, a brute force recursive solution would start at the top of the triangle 0, 0, and explore all possible paths to the bottom to compute the minimum path sum. However, this approach can be inefficient due to repeated calculations, which we address next. A critical observation is that many subproblems in the recursive solution are recalculated multiple times. For example, the function dfs I plus 1, j, might be called repeatedly for the same I, j, indices. This overlap creates inefficiency. To address this, we use memoization to store the results of previously computed subproblems. By introducing a dictionary called memo, where each key is a tuple I, j, representing a position in the triangle and its value is the result of dfs I, j, we can efficiently reuse results. Before computing dfs I, j, we check if it already exists in memo. If it does, we return the stored result directly. If not, we compute the value, store it in memo, and then return it. This optimization transforms the exponential time complexity of O2 to the power of n into a far more manageable quadratic complexity of n squared, since we now compute each subproblem only once. Additionally, this approach leverages the recursive structure of the problem, its optimal substructure, and resolves the inefficiency caused by overlapping subproblems. Edge cases, such as a single-row triangle, are straightforward to handle as we simply return the only element. It's also important to ensure our solution can handle deeper or unbalanced triangles, where rows may have varying sizes. The triangle is represented as a 2D list, where triangle I, j, denotes the value at row I in column j. The memoization dictionary, memo, plays a key role here by dynamically tracking results for all valid positions. Here's how the recursive function with memoization is implemented in Python. We first define the main function min_path_sum, triangle, which initializes the memoization dictionary and defines the inner recursive function dfs I, j. The base case checks if we're at the last row, returning the current value. For all other positions, we first check if the result for I, j is already in memo. If not, we calculate the value using the recursive formula and store it in memo. Finally, we start the recursion from the top of the triangle at 0, 0, and return the result. This approach ensures that we efficiently compute the minimum path sum while avoiding redundant calculations. The recursive solution with memoization achieves a time complexity of n squared, because there are n plus 1/2 elements in the triangle, and each element is computed only once. The space complexity is also n squared, due to the memo dictionary, though additional space is used by the recursion stack, which can go to a depth of n. To further optimize, we can implement an iterative bottom-up dynamic programming approach. This eliminates the overhead of recursion and reduces space complexity to n by reusing a single row for calculations. Let's walk through an example to solidify the concept. Imagine a triangle with the following values: 2, 3, 4, 6, 5, 7, 4, 1, 8, 3. Using the recursive approach with memoization, we would start at the top and recursively compute the minimum path sum by breaking the problem into smaller subproblems and combining their results. In the recursive execution, we begin at position 0, 0 to compute DFS 0, 0. This, in turn, requires computing DFS 1, 0 and DFS 1, 1. Each of these further breaks down into smaller subproblems until we reach the base case at the last row, where the values are directly returned. Once the base cases are resolved, we combine the results moving bottom up, calculating the minimum path sum for each position. Eventually, this process computes the overall minimum path sum for the triangle. For the example triangle, the minimum path sum is 11, achieved by following the path 2-3-5-1. This demonstrates how the recursive approach, enhanced with memoization, efficiently solves the problem while avoiding redundant computations. This implementation solves the triangle problem using a bottom-up dynamic programming approach. We modify the triangle array itself to store intermediate results, reducing space complexity to 1, since no extra space is required. The algorithm begins at the second to last row of the triangle and iterates upwards, updating each cell with the sum of its value and the minimum of the two values below it. By the time the algorithm reaches the top of the triangle, the top element contains the minimum path sum. This approach ensures an optimal time complexity of n squared, where n is the number of rows in the triangle, as each element is processed once. The solution is efficient and concise, leveraging the input structure to achieve excellent performance. This is the Java implementation of the LeetCode problem number 120, triangle. It mirrors the logic from the Python implementation provided, using Java's list structure for handling the triangle data. The algorithm iterates from the second to last row of the triangle upwards, updating each cell to include the minimum path sum from its adjacent cells in the row below. Java-specific differences include explicit type declarations, usage of the list interface, and the get and set methods for accessing and updating list elements. The final result is obtained from the topmost element of the triangle. We begin with the given triangle, 2, 3, 4, 6, 5, 7, 4, 1, 8, 3. The goal is to minimize the path sum from the top to the bottom. To achieve this, we start processing from the second to last row, which is row 2, and move upwards. For row 2, at column 0, we update triangle 2, 0 by adding its value, 6, to the minimum of the two numbers directly below it, 4 and 1. This gives us 6 plus 1 is equal to 7. Similarly, for column 1, triangle 2, 1 becomes 5 plus the minimum of 1 and 8, resulting in 5 plus 1 is equal to 6. For column 2, triangle 2, 2 is updated to 7 plus the minimum of 8 and 3, which is 7 plus 3 is equal to 10. After processing row 2, the updated triangle becomes 2, 3, 4, 7, 6, 10, 4, 1, 8, 3. Next, we move to row 1, which has two elements. For column 0, triangle 1, 0 is updated by adding 3 to the minimum of 7 and 6, the two numbers directly below it. This gives us 3 plus 6 is equal to 9. For column 1, triangle 1, 1 is updated to 4 plus the minimum of 6 and 10, resulting in 4 plus 6 is equal to 10. After processing row 1, the updated triangle becomes 2, 9, 10, 7, 6, 10, 4, 1, 8, 3.
Finally, we process row 0, which is the top of the triangle.
At column 0, triangle 0, 0 is updated to 2 plus the minimum of 9 and 10, which results in 2 plus 9 is equal to 11. The triangle is now reduced to a single value at the top: 11, 9, 10, 7, 6, 10, 4, 1, 8, 3.
At this point, the solution is complete for the first example. The minimum path sum is found at triangle 0, 0, which is 11. Moving on to the next example, the triangle is 1, 2, 3, 3, 6, 7, 4, 5, 8, 9. We start again by processing from the second to last row, row 2. For column 0, triangle 2, 0 is updated to 3 plus the minimum of 4 and 5, resulting in 3 plus 4 is equal to 7. For column 1, triangle 2, 1 becomes 6 plus the minimum of 5 and 8, which is 6 plus 5 is equal to 11. For column 2, triangle 2, 2 is updated to 7 plus the minimum of 8 and 9, giving us 7 plus 8 is equal to 15. After processing row 2, the updated triangle becomes 1, 2, 3, 7, 11, 15, 4, 5, 8, 9. Now, we process row 1, which contains 2 elements. For column 0, triangle 1, 0 is updated to 2 plus the minimum of 7 and 11, resulting in 2 plus 7 is equal to 9. For column 1, triangle 1, 1 is updated to 3 plus the minimum of 11 and 15, which gives us 3 plus 11 is equal to 14. The triangle becomes 1, 9, 14, 7, 11, 15, 4, 5, 8, 9. Finally, we process row 0. At column 0, triangle 0, 0 is updated to 1 plus the minimum of 9 and 14, resulting in 1 plus 9 is equal to 10. The triangle is now reduced to a single value at the top: 10, 9, 14, 7, 11, 15, 4, 5, 8, 9. For this second example, the solution is found at triangle 0, 0, which is 10. Now for the third example, the triangle is -1, 2, 3, 1, -1, -3. Starting with row 2, for column 0, triangle 2, 0 is updated to 1 plus the minimum of 1 and -1, which is 1 plus -1 equals 0. For column 1, triangle 2, 1 becomes -1 plus the minimum of -1 and -3, resulting in -1 plus -3 equals -4. For column 2, triangle 2, 2 is updated to -3 plus the minimum of -3 and 0, giving us -3 plus -3 equals -6. After processing row 2, the updated triangle becomes -1, 2, 3, 0, -4, -6. Next, we process row 1. For column 0, triangle 1, 0 is updated to 2 plus the minimum of 0 and -4, resulting in 2 plus -4 equals -2. For column 1, triangle 1, 1 is updated to 3 plus the minimum of -4 and -6, which is 3 plus -6 equals -3. The triangle becomes -1, -2, -3, 0, -4, -6. Finally, we process row 0. At column 0, triangle 0, 0 is updated to -1 plus the minimum of -2 and -3, resulting in -1 plus -3 equals -4. The triangle is now reduced to a single value at the top: -4, -2, -3, 0, -4, -6. The solution for this example is triangle 0, 0, which is -4. To analyze the time complexity of the solution, we observe that it uses a bottom-up dynamic programming approach by modifying the input triangle directly. Starting with the outer loop, this begins at the second to last row of the triangle and works its way up to the top. If the triangle has n rows, this loop will execute n1 times. For each iteration of the outer loop, there is an inner loop that processes all the columns in the current row. The number of columns in any row corresponds to its row index plus 1. For example, the second to last row, which is the n1th row, has n1 columns. The row above it has n2 columns, and this continues until the first row, which has just 1 column. If we sum the total number of iterations of the inner loop across all rows, it forms the series 1 plus 2 plus 3 plus n1. This series can be expressed as n1 * n/2, which represents the total number of operations performed by the inner loop. This arithmetic progression simplifies to a time complexity of O(n²). Additionally, within each iteration of the inner loop,
the work done involves updating a cell by adding the minimum of 2 adjacent values, which is a constant time operation, or O(1). Combining all these factors, the total time complexity of the solution is O(n squared). Now, looking at the space complexity, the algorithm modifies the input triangle directly, which eliminates the need for additional memory to store intermediate results. Specifically, the input triangle is updated in place to hold the results of the calculations, so no separate data structure is required. The use of auxiliary variables, such as for tracking the current row, column, or temporary values during computation, only requires constant space, or O(1). Therefore, the overall space complexity of the solution is O(1).
If we compare this dynamic programming approach to a brute force solution, the difference in efficiency becomes clear. A naive brute force approach would explore all possible paths from the top of the triangle to the bottom. For a triangle with n rows, this results in 2(n1) possible paths, as each row introduces new branching. Calculating the sum of the elements along each path would take O(n) time per path. Combining these, the total time complexity of the brute force approach is O(n*2)(n1), which is exponential and highly inefficient. Additionally, the recursion stack used during a depth-first traversal of these paths would require space proportional to the depth of the triangle, or O(n). In contrast, the dynamic programming solution significantly optimizes both metrics. The time complexity is reduced to O(n squared) by reusing previously computed results, and the space complexity is reduced to O(1) by modifying the input in place. Moreover, since the algorithm processes all rows and columns of the triangle regardless of the input, the time complexity remains O(n squared) in all cases best, average, and worst. To better understand why the time complexity is O(n squared), let's break it down mathematically. The outer loop iterates n1 times, which directly contributes O(n) to the complexity. For each iteration of the outer loop, the inner loop processes i+1 columns, where I is the current row index. Summing up all these iterations across rows results in the arithmetic progression 1 plus 2 plus 3 plus n1, which evaluates to O(n squared). Finally, the work performed in each iteration of the inner loop, such as updating a cell with the minimum of 2 values, is a constant time operation, or O(1). Combining these factors, the overall time complexity of the algorithm is confirmed to be O(n squared). For space complexity, the algorithm uses in-place modification of the input triangle and only a few auxiliary variables, such as for row and column tracking, which leads to a space complexity of O(1). This efficient use of time and space makes the dynamic programming solution highly effective for solving this problem. When solving the triangle problem, there are a few common mistakes to watch out for. One frequent issue is confusing bottom-up and top-down dynamic programming. Bottom-up is often more intuitive because you start from the base of the triangle, working upwards, which avoids recalculations. Another mistake is not handling edge cases properly. For example, small triangles with just one row or one element can lead to index out-of-bound errors if not addressed. Additionally, using plain recursion without memoization is highly inefficient since it leads to exponential time complexity due to repeated calculations of the same subproblems. Overusing extra space is another pitfall. Instead of creating a separate DP array, modifying the triangle in place is more space efficient. Finally, incorrect base cases in recursion, such as failing to terminate when reaching the last row, can result in infinite loops or incorrect answers. These mistakes are easy to overlook but critical to avoid for a correct and efficient solution. Now let's focus on some valuable insights, especially for interviews. Optimization is often a key discussion point. Interviewers may expect you to enhance recursion with memoization or suggest a bottom-up approach, and it's important to articulate the trade-offs involved in time and space complexity. Demonstrating how to solve the problem in place by modifying the input triangle shows a strong understanding of space efficiency. Another important concept is breaking down subproblems. Each cell in the triangle depends only on the cells directly below it, which simplifies both the logic and implementation. Also, being prepared to explicitly discuss edge cases is crucial. Make sure you can handle scenarios like empty triangles, single-row triangles, or very deep triangles effectively. Lastly, related problems such as minimum path sum, minimum falling path sum, and dungeon game often share similar concepts, so familiarity with these can provide additional context and problem-solving strategies. There are several approaches to solving the triangle problem, each with its trade-offs. The recursive approach with memoization improves plain recursion by caching results of subproblems, reducing redundant computations. It has a time complexity of O(n squared) and a space complexity of O(n squared) for the memoization table. Bottom-up dynamic programming is another popular method. Starting from the base of the triangle, you work upwards to compute the minimum path sum, with a time complexity of O(n squared). If you modify the triangle in place, the space complexity can be reduced to O(1). Alternatively, top-down dynamic programming involves iterating row by row from the top of the triangle. While it also has a time complexity of O(n squared), it typically requires O(n) space for a DP array. Lastly, a space-optimized bottom-up approach uses just a single row to store intermediate results, maintaining O(n squared) time complexity but reducing space complexity to O(n). Each approach has its strengths, so choosing the right one depends on the specific constraints and requirements of the problem. Great job following along. In this session, we tackled LeetCode problem number 120, triangle, and explored how to optimize recursive solutions using dynamic programming. Remember to practice similar problems to strengthen your understanding. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!